This is KBYP, and I spent a lot of time on this channel telling you that multiband antennas are a tool of Lucifer himself. They suck. Sometimes there's not much choice, especially for applications of limited space or like AM broadcast towers, where they got no prayer of matching a 300-foot tower. But I want to show you by means of the MFJ squawk box here how to get as close as possible to it. The reason hams guess at this and try to turn knobs on their magic tuner and can't get out of their own backyard without an amplifier is that they don't understand basic circuit theory. I've seen degreed engineers that could not figure this out, and that's inexcusable. Once upon a time, I didn't understand it until I stopped and thought, now think about your radio telephone training, and pop, out comes the answer. Here's a more or less electrical schematic of a dipole feed point. Not the antenna, but what appears at the feed point. And looking into the feed point with the analyzer, we should see just a 50 ohm resistance. On my 15-meter dipole, we see low SWR R45X12. That's pretty close to 50 ohms. I've changed the height. I've messed up a little bit. I've got to put it back up. It should be R50X0. A couple things to understand. We can't do this without knowing circuit theory. In a circuit, R is resistance. It takes its energy and turns it into heat. X is either inductive or capacitive reactance, or the net value of both. They subtract in a series circuit. That's conservative. Reactances don't dissipate energy. They take it from the circuit, store it in the field, then return it to the circuit, except for component losses. In an antenna, the R value is what they call the radiative portion. It's really emission. 45 represents the energy being sent out into free space. So when that's 50, all the energy from the transmission line goes through the antenna through that resistive characteristic and gets emitted into free space. That's ideal. When there's any X, which is not really reactance, it's the wire's the wrong length, something mismatched. That indicates energy that's stored cannot be emitted because it's not part of the R. It's returned back down the transmission line to the transmitter. Antennas can't store energy. They got to throw it off immediately or return it back down the feed line. Here are the basic principles. Got an R50 coax, R50 feed point. Everything's fine. Feed point can be resistive, any value. If it isn't R50, there'll be reflected energy, but that can be corrected with a matching network. If there's plus or minus X and N, X some number, for example, plus X100 is inductive, minus X100 is capacitive in a series circuit. And a dipole feed point's a series circuit. I'll explain why in a second. But that is reflected energy. That cannot be corrected. It's possible to appear to cancel it at the feed point, but it's still wasted energy. It's just not going back down the feed line. It's dissipated in matching network losses or near field losses for the antenna. The concept of magnitude impedance is R plus or minus X, and through the Pythagorean theorem, square root of the squares, which is a formula to find the hypotenuse of a triangle, we have magnitude Z is a square root of R squared plus the absolute value of the X. The absolute value just eliminates the minus sign. R is emission. X is conservative, except for losses associated with X, but it's loss. The problem here with any mismatches, these modern transmitters, like that Yaesu, have computers built in. They sense mismatch. It doesn't take but about a 1/2 to 1 SWR for that transmitter to cut the transmit power, maybe by half. So not only is a mismatch not transferring all the energy out into space, now the transmitter sees it and it says, whoa, it's mismatched. I got to protect my output circuit, so I'm going to cut the power way back. So double losses. There's no way to capture and use the energy associated with X. The R can be preferably 20 ohms, maybe 30 or more, less than 100, and be reasonably matched with a matching network, except there are matching network losses. Engineering texts reckon antenna feed point is series. How do we know that? Because that's not really an R and that's not really a C, or it could be an R or an L. How do we know? How can we prove it's series? And how do we know whether the X is plus or minus? To know that, we'd have to know whether it's series or parallel. We don't know that. Well, this is what we're not going to know unless we understand that the analyzer is freaked out. And I got to reset it. This is the kind of stuff EEs don't know. EEs get their heads stuffed full of knowledge in engineering school. They don't learn circuits, they don't learn the basics, and they go into systems. They can be systems experts and know diddle about this. Here, this 15-meter antenna is optimal when I set it at the correct height at 21.2. So that's real close. The way to determine what the X is, let's turn the frequency and get a significant X. There's X29. The formula for inductive reactance is first order linear, 2 pi FL. Inductive reactance increases with frequency. Capacitive reactance is 1 over 2 pi FC. It's a 1 over X function. Capacitive reactance increases as frequency goes down. So if we turn the frequency up, watch 21.85 and 26 ohms, we turn frequency up, 26 ohms drops like a stone. So at that frequency, at 21.8, that reactance decreasing as frequency goes up is capacitive. So that would be 105 minus, that would be 90 minus 25 there. That's a 91 ohm resistor in series with a 25 reactance capacitor. At 21.92 megahertz, that would represent a fairly large capacitance, probably 300 or 400 picofarad. Again, it's not really there. That's just the appearance at the feed point. That 25 has to go away, and there has to be some way to match that 90. That's on the 15-meter band. If we go to some other band, and we got to universally understand that the problem with a mismatched antenna is that for a dipole, it's really difficult to match an antenna that's way too short for the frequency. 15-meter dipole, 20 feet long, it ain't going to want to match on 40 meters, which where a wavelength is 120 feet. And to prove that, here's 40 meters. 1 ohm X26. Feed point, let's just call it a dead short. It will not match for any price. On 30 meters, 10.1 down where the government is. You know why they put us on 30 meters with the government services? I do. Don't interfere with them. Don't get on 30 and don't get on 60 and don't screw around with any existing radio service. They can come down on you like a hammer. 10-100. 57 x 150. Well, 57 is pretty near resistive match, but see the SWR is off the charts. That proves the 150 and extremely high SWR proves that the reactance is in series, because if the reactance was in parallel, that extremely high value would essentially disappear with regard to 50 ohms. So the impedance is increased by the reactance in series with the series circuit. Series on the left, parallel on the right. If it's parallel on the right, as that reactance value skyrockets, it becomes like it's not there. Think of how the current is going from the bottom of each diagram to the top. On the left in the series circuit, the current goes through the reactance and the resistance, so they both tend to impede it. And that's what impedance means. On 30 meters, if we could effectively cancel that reactance, and let's see which reactance it is. We'll go up in frequency and watch the 150. it goes up. So that's inductive. So on 10.1 megahertz, it's 57 ohms resistive and 150 ohms inductive. That's a series circuit on the left. If we put a 150 ohm inductor in series, that will effectively appear to cancel that reactance, but neither reactance actually went anywhere. All that does is fool the end of the transmission line to make it think that reactance disappeared. The problem is that those reactances are lossy. The antenna can't store the energy. It's not going back down the feed line now that it's matched, so it's dissipated. We haven't gained any energy coming out of the antenna necessarily. What we have done is fool the transmitter, and that's why matching is called transmitter fooling. So in circuit form, to attempt to match that transmission line, we're not matching the antenna. The antenna is going to be mismatched because it's too blasted short. But to appear to the transmission line to eliminate that reactance, we put the opposite reactance of the same magnitude between the transmission line and the feed point. So that's 150 plus 150 minus. That appears to be X0. That leaves the feed point at 57 ohms. That's so close it isn't worth arguing about. But see the magnitudes. Compare the magnitudes, 57 versus 150. Going to be a lot of wasted energy. But the transmitter is going to think it's matched. And here is where people that fall for the balun myth buy their kilowatt balun and they find that it burns up at 300 watts. It's all this reactive dissipation. It torches the toroid core. There's 20 meters. R10, real low. X25, pretty low. That 25 would not imply a tremendous reactive loss. Watch what happens when frequency goes up. Watch the R and the X. There's 14 megahertz. There's 14.1. Neither of them's changing. 14.2 changing very much. 3. Well, what's the top of the 20 meter band? 1435. At all across the 20 meter band, that feed point has changed only from 41x down to 24x. And as frequency goes up, the reactance goes up, so it's capacitive. That feed point could be tuned, so to speak, with the error variable capacitor. How much capacitance is necessary? Well, if we need 25 ohms up to 40, then for an external inductance, actually, let's see, the reactance went up with frequency, so it's inductive, so that would be correction. Since we need externally, we need a capacitance at the low end of 25 ohms and at the high end of 40 to effectively neutralize the apparent inductance. Capacitive reactance, or capacitance, is 1 over 2 pi f times capacitive reactance. Reactance is 25 ohms to 40 ohms. That works out to 450 picofarad at the bottom of the band and 280 at the top, and a small error variable. Take the difference between those, 450 minus 280. That's a 220 picofarad error variable. That's an easy value to get, and pad it with the remainder. And that would allow tuning that feed point, if you could reach it, to do that. That could be done by a small electric motor, gear motor. That ain't rocket science. But that would make that antenna work, not perfectly, but it should work reasonably on 20 meters. So let's go up and see what 17 looks like. There's 17 meters. That puppy is a dead short at 18.068 up to 168. That antenna is a dead short, both R and X. There's not a prayer it's going to work on 17 meters. There's 12 meters, 24.890. R12 X15. That X value is very low. And as frequency goes up, the X goes up, so that's inductive. That's so little, it could mostly be ignored. That's entirely a problem of an R value being too low. But that's almost entirely R. That could be done with an L network from, notice, 890, 25 megahertz. That resistance value is almost constant through there. So a L network would do to match that on 12 meters. On 10 meters, 20x62, X is decreasing as frequency goes up, so that's capacitive. Notice the reactance is flipped. So that's an external inductance. That's easy. That's just a wound solenoid coil. But notice from 28 nothing at 20x62, 21.1, 1656. Both values are going down. 1449, 12, 11, R10, 28.5, 9. That's pretty much too low at 28.8 to be useful. But there's nothing up there on 10 meters to be worth a bother to me. So I'm down here in the CW segment anyway. So that's roughly R20, and the X can be canceled by an external inductor, which is at 10 meters, that's an extremely small inductance. So very small coil. So another L network. Let's see the thing that's turning out to be a constant, which is what we look for when we do these frequency sweeps. We look for relatively small X values and R values that are relatively constant, because when the R values are fairly constant, the matching network will work a little more broad-banded. If the R would suddenly run away, it wouldn't work. The same L network can't be used on all bands. There has to be a network for each band, but it's trivial. It's easy to make them, they're cheap. Or a variable inductor and capacitor could be used, but it's a problem to put that at the feed point. There's a way around that. 6 meters. Notice the antenna has gotten quite long. As the antenna gets longer, the X values tend to decline. R11 at 51 megahertz. At 50.03, it's R13x26. 50 CW, let's see. 49, 50, 096 is a CWDX segment. 1223, up in the calling frequency, 1223. I think that passed the FT8 slot, 1220. Reactance is dropping, which means it's capacitive. Going down in frequency, reactance increases, up it decreases, so it's capacitive. But it's coming out to be 10 or so with almost no reactance. Across any part of 6 meters, I got a use for, because that's where all the action is. The top of the band is just crap, repeaters. So this antenna can be made to work on 10, 20. It already works on 15. It'll blow the radio up on 17. It'll work on 12, 10, and 6 by adding for 10 meters, a 105 picofarad external. For 20 meters, 380 picofarad. For 12 meters, I didn't figure it. For 10 meters, 280 microhenry. That's a small coil. And for 6 meters, 80 nanohenry. Correction, for 10 meters, it's 280 nanohenry, 0.28 microhenry. And for 6 meters, a tiny 80 nanohenry. Then on top of that, add an L network. But notice the resistive values are nearly constant, 10 to 20 ohms. That's a fair range. But that's a big difference between 10, 15, and 20 ohms and 50, but it's doable. There'll be some losses in the L network. Just got to live with it. There's nothing you can do about it. But for 10 meters, just an external reactance. It's already at 50 ohms. So 10 meters, 53 ohms, 150, external reactance. 20 meters, 10 ohms. 12 meters, 12 ohms, 10 ohms, 20 ohms. 6 meters, 13 ohms. So matching networks between 10 and 20 ohms, or just call it 15, and that's easy. Problem is, that's got to be done at the feed point. How do we get around that? Well, if it's a low dipole, my 15-meter dipole right now is at 5 foot 10 inches. I can just walk right out and look right at the feed point. So it's no big deal to put that at the feed point. There's a dirty little trick, if you've really paid close attention to my videos, very obscure trick, to be able to locate not the external reactance, but the matching network at the ground. The reactances at the feed point could be switched in with relays. But a transmission line might be 50 ohms. Two of them in parallel are 25 ohms. Three in parallel are 16.7 ohms, and that's right up against the R value at that feed point. So if you put that so-called canceling reactance at the feed point, that feed point could be dropped to the ground with 3 pieces of RG174 coax in parallel. And that will pretty much match the feed point. That'll bring the mismatch down to the ground. Or then you could put a variable matching network. And so that's not more weight hanging at the feed point. So there's a dirty little trick. If you really pay attention to your electrical and radio principles, you can do some neat things with this. But this will make that 15-meter dipole, which is each arm is 11 foot 7 inches, 22, 23 feet long, 6 feet off the ground. Make that work on 1, 2, 3, 4, 5, 6 bands. It's going to take a little bit of work to do it. You got to calculate L networks, but it ain't rocket science. And it's not that hard to get an air variable and make inductors or get a roller inductor. So realizing that the losses skyrocket with an X value like 150, you can't do a thing about it. But these reactances are relatively small. There's X50 on 10. That's a fair amount compared to the transmission line, but it is what it is. So if you got to have multiband for some reason, or if you just want to do what ham radio is all about, experiment, there's the big picture of how to do it. But beware, don't make the mistake that most of them do. Use ferrites at the feed point. You want to see a ferrite go up in smoke. Make a inductor with a toroid and put it at the feed point and watch it catch on fire. Because the antenna, remember the antenna is conservative. It doesn't want to emit that reactive energy. And if there's an inductor placed to cancel, that inductor core is going to take a beating. And that's, if I've heard of people, I got this 1,000 watt or 1,500 watt balun, and I have a 500 amplifier, a 500 or 300 watt amplifier, and the balun burned up. It must have been no good. No, we got an operator that doesn't understand radio principles, and the operator didn't understand core dissipation. So when you do this, they got to be air core inductors. That's going to bleed field off. It's going to be lost. There's nothing you can do about it except build a correct antenna, but at least it won't burn up. So there's how to do it if you have to do it. KBYP dit. And I made a boo-boo. The top values here are 30 meters, not 10, because I realized there were 2 entries for 10 meters. So 30, 20, 12, 10, and 6 plus 15. So 1, 2, 3, 4, 5, 6 bands. And that was at 18 minutes. Let's see, about 18 minutes in. There was also a mistake at about several minutes in where I said that the feed point looked inductive and had to use an external inductor. I got the external backwards, but that should be fairly obvious to you if you understand the concepts.